Today, we want to talk a little bit about rational functions. We want to review what we know about rational functions, maybe learn some new things about rational functions. And incorporate our calculus thinking into what we know about rational functions. So, first place to think about is, first thing we need to think about is what is a rational function. A rational function is just a ratio of polynomials. This sits in the same place as rational numbers. A rational number is just a ratio of integers. So rational functions are to polynomials as rational numbers are to integers. The polynomials are generalizations of integers. So rational functions are generalizations of rational numbers. Polynomials generalize integers. The structure of an integer is the same structure that we see in polynomials. I probably should have said it the other way. Doesn't matter. Polynomials generalize integers, so the rational functions generalize rational numbers. So rational functions generalize rational numbers. When we think about rational numbers, we're thinking of fractions. What this means is that everything that we want to think about rational functions is something that we should be thinking about fractions. All the operations that we have with fractions are going to be operations that we have with rational functions. So our operations on rational functions are just those operations on fractions. Fraction operations will be our rational function operations. Just like integer operations are polynomial operations. Once we started learning about polynomials, we weren't learning anything new. We already had arithmetic in play. We already knew arithmetic by the time we were introduced to polynomials. Once we were in our algebra class, we started learning about rational functions. We already had arithmetic of fractions in play. So rational functions use the same operations. The reason I always point that out is that it's not always made obvious to students. Most of the time, we're in survival mode in high school algebra, and so we're just trying to get by. And so when we say things like, this is just the same stuff, you're like, oh, no, it ain't. It looks different, feels different. I don't like it. I just need to know what I need to get through the test. And then later on, I'm like, oh, hey, it's all the same stuff. I'm like, oh, man, why didn't people tell me that before? Someone did. So somewhere, if every time I say something and you're like, oh man, why did my algebra teacher not tell me that? Your algebra teacher is like somewhere off in the distance going, dude, I did. I know this is true because I see it on Facebook all the time. People are like, oh, why don't you just teach it why didn't Why don't you just teach it the way I do? Why is all this face value stuff? And you look at the commenters on, I look at the commenters on Facebook, I'm like, oh, bitch, they did. You just don't remember because you haven't had to. You know what I mean? Getting the answer was never the point anyway. Besides the point. So we're not doing new things. What we know about fractions is stuff we know about rational functions. We know that when we add fractions, we need a common denominator. We know that we can cancel out common factors in the numerator and denominator. We know that if we want to divide fractions, we need to multiply by the reciprocal, right? This is all just like, those are all the operations that we're thinking of. Some of the things that I'm interested in now have to do with us understanding how graphs work for rational functions. That's actually a new thing. Fractions don't have graphs, they just constants. But as soon as I change my base from always being 10 to being x, now we get functions. We have inputs and outputs. We can build graphs. Now we're doing stuff that's new. So that's kind of what I want to talk about since we're on this connecting derivatives and graphs thing. I think this is like day 5 of connecting derivatives and graphs. So we want to think about graphs of rational functions. I think as a category, this is like derivatives and graphs. What we want to do is think about like a base model rational function. And then we're going to modify it a little bit. We're going to take what we know about functions and we're going to modify it a little bit. So first of all, the form we're going to use, a rational function, say f of x, is going to have the form p of x over q of x, where p and q are polynomials. We should note that all polynomials are also rational functions, just with a denominator of 1. Polynomials are rational functions with a denominator of 1. Just like all integers are also rational numbers with a denominator of 1. We can also describe polynomials as rational functions, except that the denominator is 1 step category. Just like integers have a denominator of 1, they're also rational numbers. The zeros of the denominator are not included in the domain of f. So the domain of f excludes any zeros from the denominator. Any zeros of the denominator are excluded from the domain of the function. Graphically, these zeros will produce one of 2 effects. This will either be a hole in the graph or a vertical asymptote. Zeros of the denominator, excluded values from the domain. Values that are excluded from the domain. Neither one very good. Anything that's excluded from the domain will give us a hole in the graph or a vertical asymptote. We get a hole in the graph if the factor the factor cancels out. We get a hole in the graph if the factor that produces that zero cancels out. We get a vertical asymptote otherwise. We have mentioned this before, but it bears repeating. So if I have the function x minus 2 over x squared minus 4, I'm just going to give the factored form. We can see that there are two excluded values. X cannot be 2 or negative 2. Those are the two excluded values. X cannot equal plus or minus 2. This is a convenient way when we want to say all real numbers except for a small finite list of real numbers. We can plug anything we want into this function except for plus and minus 2. So let's just say x cannot equal plus or minus 2. So we'll have a graph, a hole in the graph or vertical asymptote at both of these points. The x minus 2 factor cancels out. And so there's no more x minus 2. So that tells us that there's a hole in the graph at 2 and a vertical asymptote at negative 2. So the factor, if we simplify this, this is equal to 1 over x plus 2, so long as x is not 2. I can plug 2 into 1 over x plus 2. I cannot plug 2 into the original function. So I have to make a note that x can't be 2. F of x is only equal to 1 over x plus 2 when x is not 2. What this means is that we have a vertical asymptote when x is equal to negative 2. But since the x minus 2 cancels, we have a hole in the graph at 2. When I say that a factor cancels out, that's what produces a hole in the graph. That factor has to go away completely. So for example, if I have a g of x that looks like x minus 2 over x minus 2 squared, we can cancel out one factor of x minus 2, but there's still a factor of x minus 2 in the denominator. That means we're going to have a vertical asymptote at 2. Because the factor that's producing this excluded value didn't completely cancel out. It's still there. So one factor of the x minus 2 cancels, but there's still one left. How's everybody okay? We've talked about this before. We're talking about it again. Songs don't get stuck in your head because you hear them once. For those of you watching at home, it was in fact my phone that went off during class. That's the only one that ever happened. In the early 2000s, I taught at a high school, and the only phone that ever went off in class was mine. Y'all weren't in high school in the early 2000s, but it was kind of a new thing for a lot of people to be carrying around cell phones. So it became like a big deal if your phone went off in class. Teachers would like lose their fucking minds because they don't understand how reality works. Now if phones go off in class, you just like turn it off and no one bats an eye. But it used to be like a big deal. When I first started here, I was teaching over in the temporary buildings. I know we call them temporary buildings because they're like temporary buildings. Those temporary buildings have been here the entire time I've been here, and I've been here for like 25 years. How temporary are they? Are they temporary in the way that like all things are temporary and entropy takes everything eventually? Is that, I mean, geologically, is this like on a geologic scale? We're going to keep using these buildings until they fall the fuck apart because they were rusting and shit when I was here. You had to have a tetanus booster to take my class. But anyway, that's beside the point. So apparently one of the teachers that was teaching in there, that was not me, did not like students' phones to go off in class because, I don't know, some people have old people have a hard time catching up with reality. They say you get more conservative as you get older. You don't get more conservative, you stay the same. And society progresses around you. Does that make sense? The people aren't getting more conservative. It's just that society is like progressing and that person stays the same. Now, this is just as sad, but it's different. But anyway, so they wanted to remind their students to please turn off their phones because it bothered them. Now that is okay. If it's gonna bother you and you're clear about it, and you can keep yourself from losing your shit, then yeah. Just say, hey, it bothers me that, and then students be like, oh, I respect that. I will try to remember to turn my phone off. But we're gonna understand that we're all human beings, and sometimes we're gonna forget. So like, don't lose your shit if it happens. You know what I mean? Can we all just be reasonable? Apparently not. So they had to write a note. But they did a very boomer thing. They just wrote a sign that said phone. And they put it up above the board in the center. Not like, please silence your cell phones. They just wrote phone. One of my very good friends has this habit that I cannot fix. We go to a grocery store and we're looking for something, right? We're looking for chips. And you see someone that works at the store. And instead of doing the humane thing, treating the person like a human being and say, excuse me, I'm interrupting your work. So, excuse me, could you tell me what aisle the chips are on, right? That's a human interaction. That's one human talking to another human, interrupting another human in the course of their work. to ask them a question, to ask for help, to just be like, all chips? Like, is like, what the fuck? That's not a question, first of all. And second of all, show some fucking respect. You're asking for someone's help. You know what I mean? Beside the point. So it just said phone, and it was above the board in the middle. Like, the problem was it was right underneath the clock. That was mistake number one. So right underneath the clock was a sign that said phone. Second mistake, there was actually a phone hanging on the wall on the other side of the room. So I'm like, oh, I see the confusion. So I took the phone sign down and put it next to the phone and wrote a sign that said clock, and I put it under the clock. And then I made another sign that said board, and I put it under the board. I stopped it writing on the back of the card. One word is not a request. Don't be rude. I just labeled the shit in the class. I never found out who that was, so it was a night class and I wasn't here during the day. You know what I mean? There is an answer for it, by the way. If you're wondering why people my age, like Gen Xers and Boomers, just kind of like, it's lead poisoning. It's lead poisoning. We used to have lead in the gas, and that has had a negative effect on people my age. Once we started getting rid of the gas, the lead in the gas, we should get rid of the gas too. Once we started getting rid of the lead in the gas, like society in general calmed the fuck down. It was the lead the whole time. Anyway, if you're looking at an old person, they're just kind of like, just be like, oh, poor bastard, fucking lead poisoning, got this one too. Anyway, where was I talking about? Oh yeah, I got reminded that I was subjected to a huge dose of lead poisoning when I was a child. Thanks, auto industry. What are we talking about? Oh yeah, fucking graph of rational functions. So let's talk about what our basic rational function looks like, and then think about modifying it. We're going to talk about the characteristics of our basic rational function, and then think about modifying it. Yikes. This is your base model rational function, y equals 1 over x. We're familiar with this graph. We know what this one looks like. One of the things that we want to notice is that, like we were just talking about, anywhere where the denominator is 0 is an excluded value. So we see that x can't equal 0 here. We see there's nothing in the numerator to cancel out that factor of x. So that's going to mean there's a vertical asymptote at x equals 0. So we see this excluded value, x can't be 0. There's nothing to cancel it out, so there's a vertical asymptote. So we mark a vertical asymptote with a vertical line, a dotted vertical line, and say x can't be 0 on this graph. There's some other interesting things about this function. In particular, there is a horizontal asymptote. There's a horizontal asymptote. As x goes to infinity, 1 over x goes towards 0. If we if we increase the size of the denominator, the whole fraction gets smaller. If we have to divide up amongst more people, one pizza amongst more people, then each person is going to get a smaller slice. Ocean's 12 got less per person than Ocean's 11. So we also notice that there is a horizontal asymptote, since the limits as x goes to infinity of 1 over x equals 0, and the limits as x goes to negative infinity of 1 over x equals 0, we see there's a horizontal asymptote at y equals 0. So we make these very gaudy, dark, vertical dashed lines where we see vertical and horizontal asymptotes. Here are the things that we want to think about. We want to think about how we can take that vertical asymptote. What do we see in the function? What changes do we see in the function that will move that vertical asymptotes? It's a vertical line, so left and right. What will move that vertical asymptote left and right? What changes in the function will cause us to move that horizontal asymptote up and down? Oops. I didn't call it F. Heck. So what are the changes to 1 over x that will move the vertical asymptotes and the horizontal asymptotes? If you're looking at my hyperbola here and you're thinking it's not very symmetric, I cannot draw symmetric hyperbolas. I just can't. I've even tried flipping the page over. The bottom one always the top one always pushes in towards the origin, and then the bottom one is always like scooted away from, I don't know why. Probably lead poisoning. So this is the overall thing that we want to think about for while we're looking at rational functions. For today, definitely tomorrow, maybe the next day, I don't know. But this is all part of connecting derivatives and graphs. So I have a couple of functions, and I want you to do some calculus stuff on the functions, but I want you to think of it also in the context of graphs of rational functions.